In a windowless office at CIA headquarters, spring 1982, a software engineer hunches over printouts spread across his desk. 50,000 lines of assembly language for Soviet pipeline control systems, stolen and delivered by a French intelligence service 6 weeks earlier. His task is to hide a catastrophic failure inside this code without leaving a trace. Because Soviet engineers will review every subroutine, compare it against known Western systems, and test it in simulation for weeks. If they find anything suspicious, the mole who provided the shopping list dies, and the largest covert technology operation of the Cold War collapses. He picks up a red pen and circles a pressure regulation subroutine buried on page 847. Earlier that winter, French counterintelligence had walked 2,000 pages of documents into Langley. They came from a KGB colonel codenamed Farewell, working inside Directorate T, the unit responsible for stealing Western technology. The documents were shopping lists, semiconductors, turbine designs, and critically, supervisory control software for the Trans-Siberian natural gas pipeline, a 3,600-mile project meant to earn the Soviet Union billions in hard currency by selling Siberian gas to Western Europe. The lists were specific, down to manufacturer part numbers and software version designations. CIA analysts quickly understood why the Soviets needed Western software. Their domestic control systems could not manage the pressure and flow rates required for the new pipeline. Compressor stations would be spaced every 60 to 100 miles across Siberian wilderness, most of them unmanned, relying entirely on automated turbine control to maintain 1,000 to 1,200 pounds per square inch without human intervention. Soviet programmers had no equivalent system in production. Without the stolen code, the pipeline could not operate safely at the planned capacity. CIA Director William Casey saw an opportunity larger than simply blocking the theft. If the Soviets were going to steal the software anyway, why not let them succeed and deliver technology that would fail catastrophically after months of normal operation? The sabotage would look like Soviet engineering incompetence, not American intervention, and it would teach Moscow that every piece of stolen Western technology might be poisoned. Casey presented the idea to President Reagan, who authorized the operation as part of a broader campaign to feed the Soviets defective designs across multiple industries. A small group inside the Directorate of Science and Technology was assigned the task. They needed programmers who understood industrial control systems, analysts who could predict Soviet testing protocols, and targeting officers who could estimate the explosive yield of a pipeline failure in remote Siberia. The software had to match the specifications on the KGB shopping list exactly, because any deviation would alert Soviet engineers that the code had been tampered with. The team pulled legitimate turbine control software from a Western contractor and began planning the modification. The software had 3 critical functions. First, it read pressure sensors at each compressor station and adjusted turbine speed to maintain pipeline pressure within safe limits. Second, it detected anomalies, abnormal vibration or temperature, and initiated emergency shutdowns before equipment damage occurred. Third, it logged operational data for remote monitoring by Soviet pipeline engineers hundreds of miles away. The system had to operate autonomously in sub-zero temperatures for months at a time because resupply missions to the remote stations were expensive and infrequent. Any failure in simulation would be obvious. The team knew the Soviets would run the software through exhaustive simulation. KGB technical reviewers would compare the code structure against known Western systems to verify it was genuine. Soviet pipeline engineers would simulate thousands of operational cycles, checking that turbine responses matched expected behavior under varying load and temperature conditions. If the software crashed, produced implausible outputs, or contained undocumented subroutines, the entire operation would be exposed. The malicious code had to survive scrutiny from 2 independent groups of engineers, neither of whom could suspect sabotage. The first obstacle was KGB Line X, the Technology Acquisition Unit. Their officers were trained to detect poisoned technology, a known Western counterintelligence tactic since the 1970s. They would compare the stolen software against published technical papers, patent filings and known installations of Western pipeline systems. If the code contained functions that did not appear in legitimate systems, or if documentation was inconsistent with the manufacturer's standard practices, Line X would flag it as suspect and interrogate the source. The software had to be indistinguishable from a genuine product. Even the method of creating the malicious code posed risk. Software compiled from high-level languages often left artifacts, patterns in the binary that revealed the compiler version and settings used. If the CIA team compiled their modification using a different toolchain than the original vendor, Soviet analysts might notice discrepancies in instruction sequences or memory allocation. The engineers decided to hand-code the malicious subroutine directly in assembly language, matching the style and structure of the surrounding code so closely that it would appear to be part of the original design. The second major constraint was timing. The CIA could not predict when the Soviets would complete pipeline construction and begin full operations. A logic bomb triggered by calendar date might detonate during testing, causing minor damage and maximum suspicion. Or it might activate years too late, after the pipeline had been debugged and the Sabotage software replaced. The trigger had to be tied to operational state, not time, something that would activate only after the pipeline reached production capacity and ran continuously for weeks. The explosion had to appear plausible as a Soviet engineering mistake. If the failure mode was physically impossible under normal operating conditions, or if forensic analysis revealed deliberate sabotage, Moscow would understand the technology had been poisoned and might retaliate militarily or expose the Farewell mole in a show trial. The CIA targeting analysts studied Soviet pipeline construction standards and identified failure modes that matched known defects in Soviet welding practices and quality control. The sabotage had to exploit a weakness the Soviets would believe was their own fault. Soviet engineers would simulate weeks of operation before deploying the software. The code had to produce correct pressure readings, appropriate turbine adjustments, and realistic log files for thousands of cycles. Any divergence from expected behavior during simulation would trigger debugging, and a thorough debugging session would expose the hidden subroutine. The malicious code had to remain dormant, executing no unusual instructions and leaving no memory footprint until the trigger condition was met. It had to be, in effect, invisible until the moment it was too late. The team settled on a cumulative trigger. The malicious code would track the integral of pressure over time, a value that increased only when the pipeline operated above a certain threshold for extended periods. During testing, pressure would cycle up and down, never accumulating enough pressure hours to activate the bomb. Only a fully operational pipeline, running near maximum capacity day after day, would cross the threshold. The exact value was calibrated using stolen Soviet pipeline specifications and estimates of how long Moscow would run the system before routine maintenance. The engineers faced a final, irreversible constraint. They could not test the modified software on actual Soviet pipeline hardware because they had no access to it. They could simulate the trigger logic on paper and run the code through Western control systems, but they could not verify that the malicious subroutine would behave correctly under the specific conditions of a Siberian compressor station in winter. The modification had to work on the first attempt, with no opportunity for iteration or debugging. Once the Soviets stole the software, it was beyond reach. Spring 1982. The CIA selected a Western contractor known to supply pipeline control systems and known to have poor operational security. The modified software was staged to appear on the contractor's network as a current product version, complete with documentation, update logs, and licensing files that would pass KGB review. The agency could not approach the contractor directly because any warning about an impending theft would alter the contractor's behavior in ways that might alert KGB surveillance. The software had to be stolen, not handed over. The KGB conducted weeks of surveillance on the contractor. Line X officers identified employees with access to software development systems, tracked their routines, and assessed which individuals might be vulnerable to recruitment or blackmail. The CIA observed this surveillance through its own counterintelligence channels, but took no action that would disrupt it. The theft had to unfold using standard KGB tradecraft because any deviation from their normal operational pattern might suggest a setup. The agency waited for the Soviets to make their move. The Soviets penetrated the contractor's network and exfiltrated the software. According to intelligence reporting, the operation used a combination of recruited insiders and remote access, typical Line X methodology. The stolen files included source code, compiled binaries, and technical manuals, all of which matched the specifications on the Farewell shopping list. The KGB transmitted the data through encrypted channels back to Moscow. The CIA confirmed the exfiltration through signals intelligence, but did not intercept or interfere. The trap was sprung, and the software was now in Soviet hands. Within days, Farewell's intelligence stream confirmed the software had arrived in Moscow and passed initial KGB technical review. Line X analysts found no anomalies in the code structure and no documentation gaps. The software was assessed as genuine and forwarded to the Ministry of Gas Industry for deployment on the Trans-Siberian pipeline. The CIA team received the confirmation through French intermediaries, coded in Farewell's regular reporting. The mole had done his part, and the software was moving toward the field. The software traveled east to the Urengoy region of western Siberia, the heart of the new pipeline project. Soviet engineers installed it on control systems at compressor stations along the route, stations spaced roughly 70 miles apart across taiga and tundra. Each station housed turbines the size of a bus, powered by a fraction of the gas they compressed, and linked by fiber optic cable to a regional monitoring center hundreds of miles away. The software went live in the spring and began controlling pressure across the network. The CIA lost real-time visibility. Farewell could not report on day-to-day engineering activity without compromising his position inside the KGB. Satellite reconnaissance could track construction progress, new buildings and pipeline sections, but could not see inside control rooms or read software logs. The agency did not know whether the Soviets were running the code in production or still testing it, whether they had encountered bugs and begun debugging, or whether the trigger was accumulating its pressure time integral toward activation. The team could only wait. Weeks passed. Satellite imagery showed accelerated construction activity along the pipeline route. New compressor stations appeared, pipeline sections were welded together, and ground disturbance indicated trenching for fiber optic lines. Intelligence analysts estimated the Soviets were moving toward operational testing, meaning the software was likely controlling live turbines under partial load. The pressure time integral would start climbing as soon as the pipeline reached sustained operational pressure. The clock, such as it was, had started ticking. The operation was irreversible. The CIA had no mechanism to recall the software, no way to signal the Soviets without exposing the Farewell source, and no means to predict the exact moment the trigger would activate. If the logic bomb failed to detonate, the Soviets would operate a functional strategic pipeline for decades, and the entire Farewell Dossier operation would yield no visible result. If it detonated during a maintenance window or in a populated area, the consequences could escalate beyond economic sabotage. The team had committed, and the outcome was now in the hands of physics and Soviet engineering schedules. The logic bomb was embedded in a subroutine responsible for pressure regulation. Under normal operation, the software read sensors every few seconds and adjusted turbine speed to hold pipeline pressure between 1,000 and 1,200 pounds per square inch. If pressure climbed above 1,200, the turbine slowed. If it dropped below 1,000, the turbine accelerated. The malicious code added a hidden counter that tracked the cumulative product of pressure and time. Once that integral exceeded a calibrated threshold, the software began ignoring high-pressure sensor readings and instead incremented turbine speed, overriding the safety logic. The drift was subtle. The software increased turbine speed by fractions of a percent per cycle, small enough that no single sensor reading would trigger an alarm. Over the course of hours, however, the compressor station pushed more gas into the pipeline than downstream stations removed, and pressure began to climb. The system's alarm thresholds were set for rapid spikes, not gradual accumulation. So Soviet operators monitoring the remote station saw fluctuations within what appeared to be normal operating variance. By the time pressure reached 1,400 pounds per square inch, the pipeline was already outside its design envelope. Pipeline steel is rated for hoop stress, the circumferential force exerted by internal pressure. Soviet pipelines of this era used steel rated for roughly 1,200 to 1,300 pounds per square inch, with a safety margin above that before yielding. At 1,500 psi, the steel began to deform. Microscopic cracks appeared in welds, points where the crystalline structure of the metal was slightly weaker due to thermal stress during fabrication. The pipeline did not rupture immediately, because steel fails gradually under sustained load. But the process had started. At approximately 1,500 pounds per square inch, a weld seam near the compressor station failed. The failure propagated along the weld line in milliseconds, and a 6-foot section of pipe opened like a zipper. High-pressure natural gas, roughly 95% methane, vented into the atmosphere at a rate estimated at several million cubic feet per minute. The gas was cold, minus 20 degrees Celsius from adiabatic expansion, and formed a visible white plume as water vapor in the air condensed. The compressor turbine continued to run, feeding the rupture, because the malicious software was still overriding the emergency shutdown logic. Natural gas is lighter than air and normally disperses rapidly, but in calm wind conditions or confined terrain, it can accumulate. The compressor station sat in a shallow valley, and the gas formed a vapor cloud hundreds of feet across, mixing with air until it reached a concentration between 5 and 15%, the explosive range for methane. The cloud was invisible, except for condensation fog at its edges. It drifted slowly downwind, still fed by the ruptured pipeline. The compressor turbine's exhaust and ignition source was roughly 50 feet from the breach. The ignition source, likely a static spark or hot surface from the turbine exhaust, ignited the vapor cloud. Because the methane-air mixture was near stoichiometric ratio, the combustion transitioned almost instantly from deflagration to detonation, a supersonic shockwave propagating through the cloud. The explosion released energy equivalent to roughly 3 kilotons of TNT, comparable to a small tactical nuclear weapon, but without radiation. The compressor station vaporized. The pipeline ruptured for miles in both directions as the shockwave propagated through the pressurized gas inside the pipe, turning the pipeline itself into a linear fuel source. American early warning satellites, part of the Defense Support Program, detected the explosion's infrared signature within seconds. The satellites were designed to spot Soviet ICBM launches by detecting rocket exhaust plumes, and the pipeline fireball was orders of magnitude larger than a missile plume. The thermal bloom saturated the sensor, producing a signature initially indistinguishable from a low-yield nuclear detonation. Ground stations relayed the alert to NORAD headquarters in Colorado, where analysts began calculating the yield and checking for radiation signatures that would confirm a nuclear event. Summer 1982, NORAD analysts calculated the yield and confirmed no gamma ray or neutron signature, ruling out nuclear fission. The explosion was non-nuclear, a massive conventional event, but the location was inside Soviet territory near known strategic installations. The alert was downgraded from nuclear threat to anomalous event and forwarded to intelligence channels. CIA headquarters received the notification within minutes. The targeting coordinates matched a compressor station on the Trans-Siberian pipeline. The team that had modified the software realized the logic bomb had likely detonated. The CIA could not confirm whether the logic bomb had triggered or whether the explosion was a legitimate Soviet engineering failure. The satellite data showed the location and yield, but could not reveal the cause. There was no way to inspect the wreckage without exposing American intelligence interest in the site. The team debated activating Farewell to request confirmation, but the risk was too high. If the KGB was already investigating Sabotage, any unusual query from Farewell would link him to the incident and expose the entire Farewell Dossier operation. American signals intelligence intercepted Soviet military and KGB communications in the hours after the explosion. The intercept showed confusion and urgent damage assessment, but no immediate accusation of sabotage. Soviet commanders were trying to understand whether the explosion was an accident, a structural failure, or a deliberate attack. The tone suggested they were treating it as an internal engineering problem, not an act of war. This was a critical indicator, because if Moscow suspected American involvement, the intercepts would have reflected preparations for retaliation or diplomatic escalation. The CIA decided not to activate Farewell. The intelligence value of confirming the trigger was outweighed by the risk of losing the source. Farewell was reporting on broader KGB technology acquisition operations, and he was more valuable alive and undetected than as a single-use asset to confirm one explosion. The decision meant the team would never know with certainty whether their logic bomb worked or whether the Soviets had simply built a defective pipeline. The ambiguity was the price of protecting the source. The Soviets shut down the entire affected section of the pipeline and began a forensic investigation. Intelligence indicated they were focusing on weld quality, pressure sensor calibration, and operator training, all plausible failure modes for a Soviet construction project. There was no indication they were reviewing the control software for malicious code. Over the following weeks, the Soviets replaced damaged pipeline sections and rebuilt the destroyed compressor station, but they did not immediately resume full operations. The project was delayed by months. Within weeks, intelligence reporting indicated the Soviets were attributing the explosion to a combination of construction defects and operator error. Official Soviet records, to the extent they existed, did not acknowledge the explosion publicly. Western intelligence estimates of the damage came from satellite imagery and signals intercepts, not Soviet statements. The lack of public acknowledgement suggested the Soviets were treating it as an embarrassing failure rather than an international incident. The CIA operation had achieved its goal. The sabotage looked like incompetence. The explosion destroyed the compressor station completely and ruptured the pipeline across a section estimated at several miles. The Soviets had to replace not only the station, but also inspect and repair welds along adjacent pipeline segments to ensure no additional damage from the shockwave. The delay set the Trans-Siberian project back by months and cost the Soviet Union significant hard currency in lost gas sales to Western Europe. Satellite imagery confirmed reconstruction activity continued into late 1982, but the pipeline did not reach full operational capacity until the following year. Farewell continued reporting until November 1982, when the KGB arrested him on unrelated counterintelligence grounds. The arrest was not directly linked to the pipeline explosion, but to broader KGB internal security sweeps. He was tried in secret, convicted of espionage, and executed in 1985. The CIA lost its most valuable source inside Soviet technology acquisition operations. French intelligence, which had managed the Farewell case, confirmed his death through their own channels. His identity, Vladimir Vetrov, remained classified for years after his execution. The pipeline incident was one operation within a broader campaign. Using intelligence from Farewell's documents, the CIA fed the Soviets sabotage technology across dozens of targets. Flawed microchip designs that failed after months of use, turbine blueprints with incorrect tolerances, and chemical plant specifications that produce substandard materials. The goal was to waste Soviet resources and slow technological development by turning their own espionage apparatus into a distribution network for defective designs. The campaign extended beyond software into hardware, manufacturing, and industrial processes. Reagan administration officials later credited the Farewell Dossier with accelerating Soviet economic decline. The campaign forced Moscow to waste billions of rubles on technology that did not work, and to invest in expensive domestic research and development to replace systems they thought they had already acquired. According to declassified assessments, the operation contributed to the broader strategy of economic pressure that complemented military competition and arms control negotiations. The pipeline explosion became a symbol of the campaign's reach, even though the details remained classified. The pipeline incident established a Cold War precedent. Sabotage could be delivered through the supply chain itself, making every piece of acquired technology a potential liability. The operation demonstrated that an adversary's own acquisition effort, the espionage and procurement network, could be turned into an attack vector. This insight became foundational to later cybersecurity and counterintelligence doctrine. The idea that the supply chain is a battlefield, not just a logistics problem, traces directly back to operations like this one. Modern cybersecurity treats supply chain integrity as a critical vulnerability. Software provenance, hardware component verification, and vendor security assessments are now standard practice, directly informed by the recognition that adversaries will target acquisition and procurement. The National Institute of Standards and Technology, the Department of Defense, and intelligence agencies all maintain supply chain risk management frameworks that assume components and code may be compromised before delivery. The Cold War lesson, that the acquisition process itself is an attack surface, remains central to defensive planning. The operation remains partially classified. Some details appear in memoirs, declassified CIA documents, and National Security Archive releases, but these sources sometimes conflict. The exact software modification has never been publicly released. The precise date of the explosion is reported variously as June or July 1982, and the exact compressor station location within the Urengoy region varies by source. The explosive yield, often cited as 3 kilotons equivalent, is an estimate, not a measurement. The operation's success is clear, but many specifics remain behind classification barriers. Popular accounts sometimes describe the incident as a cyber attack, a computer virus that blew up a Soviet pipeline. The reality is more grounded. The CIA modified control software to mimic a plausible engineering failure, delivered it via human espionage, and timed it to activate only after months of normal operation. It was not a virus spreading through networks, but a targeted modification inserted into a specific system the Soviets were known to be stealing. The operation succeeded because it exploited human intelligence and physical infrastructure vulnerabilities, not just software. The operation demonstrated that software controlling critical infrastructure can fail in ways that appear accidental. The malicious code survived review and testing because it mimicked legitimate logic and produced normal outputs until a specific operational condition was met. This principle, that code can contain delayed failure modes indistinguishable from bugs, remains relevant to industrial control system security. The lesson for defenders is that thorough code review and testing may not detect adversarial logic designed to activate only under rare or sustained conditions. The operation succeeded because the CIA protected the source at every stage. Farewell's intelligence enabled the entire campaign, but the agency never activated him for confirmation of the pipeline explosion, prioritizing his long-term value over short-term certainty. The decision to let the Soviets steal the software using their own methods rather than handing it over preserved the illusion that the technology was genuine. Operational security, the discipline of protecting sources and methods even when it limits immediate intelligence gains, was the foundation of the operation's success. The software the CIA modified in that windowless Langley office in 1982 worked exactly once. It passed Soviet review, survived testing, activated on schedule, and produced an explosion visible from space. Then it was gone, destroyed in the blast it created or replaced during the Soviet investigation. The engineers who wrote it never saw the result firsthand, never inspected the wreckage, and never confirmed with certainty that their logic bomb was the cause. But the pipeline exploded, the Soviets blamed themselves, and the operation remained secret for years. In the silent calculus of Cold War sabotage, that was success.